So, a very good morning to everyone, and a very warm welcome to the sixth session of Semiconductor Nation Campus Connect webinar series, which is an initiative under Semicon India Future Skills by ISA. So, in this webinar, our intention is to cover the entire spectrum the entire spectrum of how it starts from the sand and how how the journey happens and what are the processes which are involved into this journey, so that things will be shared with the expert here. So you can see this slide where we have covered the spectrum of the pictures that will help you walk through this journey. So we'll be covering one block, or if we being a little bit of precise, we will be breaking few blocks into multiple sections as well, where the experts will be talking to you about the various things, various type of skills needed, what happens in that, how you could be preparing yourself for that. So those things will be discussed there. Uh, and also, in the previous sessions of this series are recorded and they are archived and they are saved on Nexa's YouTube channel. You can anytime go back and watch them as and when you feel like, or as and when you are interested, or as and when you have the time to go back and walk through those pictures. And also, this session will be recorded and it will be maintained in the same archive folder there. And these sessions can also be used by the faculties as a part of their lecture, as and when they find it suitable in the course curriculum. Also, please put your thoughts and questions in the chat box, and those will be discussed towards the end of the session. So in the last session, we walked through that about the SoC verification, precisely about what and why part of it. And as promised in the last session, we are back here again, where we'll get to know about how part of SoC verification. So with that, it gives me an immense pleasure to again introduce you to our today's speaker, Mr. Ravindra Pal Singh. He's an semiconductor industry professional with more than 25 years of experience in the VLSI design industry. He's currently associated with ST Microelectronics as a senior group manager, and he has graduated from NIT Kurukshetra and holds expertise in SoC design. Most of his experiences have been in functional verification, both at IP and SoC level. So, a very, very warm welcome to Mr. Singh, and over to you.
Thank you, Sushma. I'll just start my video. Okay, and I will share my presentation. Moment.
We can't hear you.
Am I audible now?
No.
Yes, we can hear you.
Okay. So let me share. Go into the presentation mode. Okay.
Okay.
So good morning and very warm welcome to all my friends who have taken the time to tune in into this session today. So this is a follow-up session on SoC verification overview. We had one session last month, and this is part 2 of that session. In part 1, we had discussed about the introduction to verification and SoC verification specifically. And we had covered the why portion. We had discussed on why verification is important and why is it absolutely necessary that we ensure that no bugs reach silicon, because we know that our customers expect flawless operation from the devices, electronic devices that they have spent money and purchased. So, and on the what portion, we discussed what is functional verification, the basic concepts, and what is it that we want to cover um, uh, at SoC level when we talk about functional verification of SoC. In this part, we will cover the how aspect of this topic, and we will discuss how things are actually done, what are the tools, techniques, etc. covered, and how functional verification is actually achieved. So these are the topics that I will cover in this talk. We will talk about languages, tools, and methodologies that are involved. Following this, we will discuss the test bench approaches, uh, test benches that can be created using these languages. Following this, we will talk about simulations and how we debug things in case they fail. We'll cover the three techniques that are popular in verification: simulation, formal verification, and assertion-based verification. We will cover how verification is measured and how do we actually track the progress of verification. Then this will be followed by quality metrics and when do we say that we can actually sign off on verification and then we are done. We will also cover emerging trends that we are seeing in this industry from verification viewpoint. And finally, I will share my observations with you all. So languages, tools, and methodologies. When we talk about verification today, we almost always mention system Verilog, because system Verilog is a language of choice and it's a de facto verification, de facto language, de facto standard language in which verification environment is coded today. We will discuss more about this in following slides. Now, based upon this system Verilog is a methodology, a framework that is created, which is used for verification. And this is called Universal Verification Methodology. Other languages are C and assembly also. So these are also used to verify in certain kind of test benches, which we will also discuss to verify especially core-based SoCs. The minimum set of tools that we need for verification function is the simulator. We'll talk more about this also. We need waveform analysis and debug tool. We need coverage analysis tool. And if we deploy formal verification, we will also need a formal verification tool. So these are the minimum set of tools that are needed in order to achieve verification. System Verilog and UVM, or Universal Verification Methodology. So what is System Verilog? To understand what is System Verilog, let's first discuss what is Verilog HDL. So we discussed in our previous session that we need a hardware description language in order to describe our designs and also to describe the SoC. So this falls under HDL, or hardware description language. And just a trivia around HDL, Verilog HDL was actually created in mid-80s, and this was the credit for invention of Verilog HDL goes to an Indian, which is Dr. Prabhu Goyal and his team. And in his company, they invented a method to describe the hardware in a high-level English-like language, which we know as Verilog HDL. So this was around middle of 80s. And then this language became really popular in the industry, and it was adopted as IEEE standard in 1995. And there was, of course, a revision in 2005. Now, this is on the design side, how we describe the design. And during that time, also very basic test benches and verification was also done using Verilog HDL. But majorly, this language was custom made to describe the designs, the sequential and the combinational logic in the design. Now, also in parallel to this, there was activity on verification, because verification needs more complex features, and in order to create randomized stimulus, in order to create test benches, more flexibility. And what was happening in parallel to this was that hardware verification languages were being developed, and there were many languages which were there. Some of them were Vera or eSpecman. So a lot of hardware verification languages were there, and these had what we call features. These look more like object-oriented programming languages, like C++ we know today. And with all the inherent advantages of object-oriented programming languages, and were much more feature-rich and complex compared to HDL, because their purpose was different. Their purpose was to actually create a test bench around the design. So the HVL languages, hardware verification languages, were then standardized standardized by IEEE, and this was standardized at IEEE 1800 in 2005. Now, what happened after that was that the industry didn't really want two separated IEEE standards to work with, and they said that why don't we combine the two standards into one IEEE standard, and that can be used as a unified standard for both design as well as verification. So that happened in 2009, when HDL branch was actually merged into HVL branch, and that led to the creation of IEEE standard 2009. And then it was revised again in 2017, and this is what we today call as IEEE standard of system Verilog, which is a unified standard, and it has all the features using which you can do either design or you can do verification. So this is system Verilog. Now, let's try to understand what is UVM. When you give a language which is as rich as system Verilog, you give it to engineering teams and you ask them to verify their designs. So what happens is that the teams will use this language features, because it's a very rich language features. So they will use that to create the environments for their own purpose, and which will do their job in a very good way. But the problem is that different teams will use the language to create their test benches or their environments in different way. So different teams, even within the same company, will create their environments which will look pretty different. And the issue with this is that there is no reuse, and the cost of verification is high. And why it is high? Because there is no sharing. If team A wants to share their development with team B, it cannot be done, because team B has an environment which looks completely different than what team A has. So there is no reusability, there is no sharing between teams, and even in the same company and across the industry also. So this leads to high cost of verification. This was the problem which was understood by the industry, and they said that why not standardize the way how things are done, not just the language, but also the way to create the environment. Why not standardize that? So this led to the development of again a standard, IEEE standard for methodology, and this was the first effort by the industry to standardize a methodology, not just language, but methodology, the framework, how things should be done. And they standardized the framework as basically it is a the standard describes the set of base classes or infrastructure with very standard APIs, very standard function calls, function names. It's a framework which you can use and to create your environment. Now, what this led to? This standardization led to different teams creating their environments which was compliant to UVM or Universal Verification Methodology, and now their environments looked very much similar to each other. And what this brought about in the industry was reusability in interoperability. So the teams could now share their development with each other, and every team did not have to invent the wheel again if they were verifying the same thing, if they were trying to do the same thing. So there was a lot of sharing, reusability, and also it led to development of let's say the vendors who could actually create components which were compliant to the standard, and then supply it to and sell it to different companies. So it led to development of standardization, reusability across the chip design industry. And this is the main reason why UVM was standardized. And this is the main USP or unique selling point of UVM. Now, let us see the test bench approaches. We have the languages, we have system Verilog, we have a methodology, which is UVM. Now, next thing we want to create is a test bench to verify our DUT. So this is our SoC, design under test, which we want to verify. And next thing is to create a test bench around it, which is UVM compatible in this approach. So let's say we have to verify a UART block, which is in this SoC. What you will need to do is that create the monitor the inputs and the outputs of UART, and then send it to the test bench, which can compare the inputs and outputs and then say whether the block is working correctly or not. Now here, the key point is that you see the structure of these components. So let me just structure of these components. So in UVM parlance, we have standardized nomenclature, we have UART agent. So you would actually hook up a UART agent to the UART outputs, which are monitoring the UART ports here. And it has got a standard structure, which means that it has got a monitor, a driver, a sequencer, and we call it agent. On the other side of UART, also there is a similar structure. We have driver, monitor, sequencer, which is monitoring the other side of the UART, and then we have a scoreboard, which is kind of a comparator between input and output, and which does the actual checking. And we also have coverage elements. And all this is bundled together into what we call in UVM an environment. And in this case, it is a UART environment, ENV for short. So, with this component, UART environment, the UART block can be verified. What is also needed additionally is to drive the UART, because how we want to verify? We want to let's say we want to write a character into UART, and which gets transmitted over the transmit line, and then check whether it's happening correctly or not. So for that, we also need one component to replace the processor. And again, this is in a standard, if it's a UVM compliant, it is in a standard structure. Again, a monitor, driver, sequencer, and we call it as a processor agent or processor bus functional model. What it will do is it will write a character, let's say A, over this bus, into the UART block, which will transmit it over transmit line. And here the UART agent is set up to actually echo whatever it receives on the transmit to the receive. So it echoes back the A character on the receive. UART receives it. It generates an interrupt to the processor agent, and then the processor reads from the UART that what character it has received. And if it receives an A, that means the UART must be functioning correctly, because A was what was transmitted and A is what is received. So using this infrastructure, UART block can be verified. Now, now what is the advantage? Advantage is, let's say some other team in the same company also wants to verify UART because they have a UART on their chip. Simply, they can get this UART environment from the team that has already got it, and then hook it up into their test bench, which in a matter of hours, and then they are all set. They don't have to create the UART environment again. This is the advantage of UVM. And same goes with other components like processor agent also they can reuse. And likewise, so stimulus generation and checking is done. So we already discussed that. Likewise, there can be environments for other IPs. Let's call it IPX environment. So all the IPs will have similar looking structure, and they can be shared freely with other teams. They can be developed even by third-party companies and bought and sold, as long as they are UVM compatible. So this is how industry-wide reuse, company-wide reuse is enabled by UVM. Now let's come to another popular approach, which is C and UVM based. Here again, we have to verify same DUT. Let's again assume that we have to verify UART block using this test bench. So in this test bench, the stimulus generation and checking is done using C code executing on the processor. Now, we all know that how C code works, right? So verification engineer would write a C code to transmit, receive, and check from the UART. And this is compiled by the toolchain, the compiler, linker. Normally, it's a freely available GNU compiler. And then it's converted to hex, and it is loaded into RAM. So once the chip is out of reset, processor starts to execute this code and starts to execute this code. What is also needed in addition to the C code that processor executes is also similar UART agent on the UART lines. And why this is needed? Because let's say the engineer has written to write a character A into UART, and processor executes that code from the RAM, and the character A is written into UART. It is transmitted. Now we need some agent in the test bench to monitor that, and then we have to set it up again to echo that back into RX. So whatever is received on the transmit line is echoed back into receive line, and thus the A character which was transmitted is looped back into UART. UART again interrupts the processor. In this case, this is the actual processor HDL, and it services this interrupt by reading the UART receive register and then compares it with again A. So A was transmitted, A was received, same as in previous test bench, but in this case, the processor is running actual C code, and there is still a UVM component which we need in the test bench to handle the TX and RX of UART. So this is a combination of C and UVM test bench, which is being used to verify the UART block. And likewise, we will have components of other IPs let's call it IPX, and again standard looking component, and like that we can have other components. So this is another popular test bench approach. Now we have created the test bench and we know how to write test cases. We have written the test cases. Let's say the next thing is to simulate the test bench and see what is happening. So for this, we need the simulators. If you see the dictionary definition of simulation, it says it is imitation of situation or process as it would happen in reality. So what simulators help us to do is to visualize what will visualize in the software world what will actually happen in the actual physical IC. So that is what simulators do. And there can be two types of simulators, digital or analog. Digital simulators are event-based. What that means is that whenever there is a change in any signal in the HDL of the SoC, the simulators are kicked into action and they calculate the values of all other signals in the SoC. So just to calculate the effect of this signal change to all other signals in the SoC. So this is what we call event based simulation. So any event leads to simulator kicking in and calculating the values of all other nodes in your design. Analog simulation, on the other hand, is time-based and is more slower because, and what I mean by time-based is that contrasted to event-based simulation, analog simulation would calculate the values and solve the circuit at every time point. Let's say it's after every 10 picosecond, they will analog simulator will calculate and solve the entire analog circuit using all the laws like Kirchhoff laws. It will calculate voltage, current, etc. at every time point, and that makes the analog simulation very slow in comparison to digital simulation. But analog simulation is also deployed in certain cases where we need the accuracy of analog simulation. But mostly in SoCs with digital content, what we use is digital simulators. We use what we described in previous session as digital mixed signal simulation, DMS, with analog blocks modeled as a real number models. So mostly digital simulations in chips with digital content. And in very specific cases, analog simulation is used, mostly by the analog design teams. Okay, so we have done the simulation. We have got the test bench, we simulated it. And what we need next is if something fails, or we need to visualize what is happening within the design, we need waveform viewers. These are absolutely indispensable for debugging. So this is an example of a waveform viewer where after simulation, we can bring up the waveforms and we can see exactly what is going on inside the design. Each signal can be shown in this waveform viewer, and if something is failing, or if you want to analyze the waveforms, we absolutely must have this. And contrast this with debugging on silicon. On silicon, we don't have this facility. We don't have internal visibility into internal nodes of a physical device. But in the simulation world, we have complete visibility. And we can see what's going on inside and see whether it makes whether it is behaving as expected, and we can debug things. So absolutely essential to have a waveform viewer tool. Okay, so now we move to verification approaches. Simulation. Simulation is the baseline approach and to verification. And of course, by baseline is that this has to be there. So simulation is a must-have. And let's try to understand how this works by taking again the example of UART IP. Let's say our specification is that the UART should support characters A, B, C, D, E, 5 characters and 2 baud rates. And our verification goal is to check that this functionality is working correctly. UART transmit functionality. Very simple and intuitive approach is to do a directed stimulus for this. Here, what a verification engineer would do, right? He would simply have 2 variables, transmit character and baud rate, and then write a code to cover all the 10 combinations of transmit character and baud rate, and then run the simulation. So here, most of the work is actually being done by the verification engineer by coding all the specific cases which he or she wants to cover. And so this arrow shows the effort. So there is high effort on the verification engineer side, and the machine is running simulation. Directed verification approach. So this is a conventional approach which has been around for years and years together, and this is now considered more or less obsolete. Okay, so it is still used, but only in specific cases. But generally, this is not the main approach for verification. So research in verification has always been uh, on how to reduce the effort on the verification engineer side and how to increase the quality. And that research has resulted into development of another approach, which is constrained random stimulus approach. So here, what happens is that the coding is done just once and the machine does the rest. So let us see how. So in this case, all we do is that we use system Verilog features, again 2 variables, but now we define them as random variables. So random variables character, transmit character, random variable baud rate, and then we describe the constraints of these 2 variables. We say that transmit character must lie inside A to E, and likewise baud rate must lie inside 9.8 and 9.6, just 2 values, one of the 2 values. And then we run this particular test 10 times on the server. And what the machine or the tool will do, every time this test is run, it will select one value from transmit character, one value from baud rate, and that way it will cover all 10 combinations. So it is coding once, but running 10 times. So obviously here we see that there is now more lesser work on the verification engineer side because the code is reduced now, and we are asking machine to do all the 10 combinations. So this increases the intelligence of verification, intelligence in the verification process, and utilizes the machine time to do most of the work. And one added advantage is that this is a simple example, but if you have a complex set of cases where you have many variables, then the randomization between those variables can lead to creation of scenarios which are really corner case, which is very difficult to think and code by the verification engineer using the directed approach, because then everything depends upon the verification engineer's imagination, creativity on whether he or she can hit that particular case. But in a constrained random stimulus approach, machine can come up with such scenarios, such corner cases, and can expose some really hard to find bugs. So with constrained random stimulus, what has been achieved is a reduction of effort on the verification engineer side and also improvement of verification quality in terms of hitting corner cases bugs. So this is the standard approach which is followed across the industry now. And directed stimulus approach is used only in specific cases. Moving on to another approach which is formal. So further research into verification to answer these questions, right? How can we reduce the effort on the verification engineer more and make the servers do more, right? And more intelligence on the verification engineer side and in the whole verification process. So that research also led to development of another approach, which is formal verification approach. And this is fundamentally different approach than simulation. In simulation, tests are being written by the verification engineer to prove the presence of bugs. So that means engineer is trying to hit the bugs, where bugs could be there, and then code a test case and then simulate and prove that there is a bug there. In formal verification approach, it is fundamentally different in the sense that it ensures that it tries to prove that there are absence of bugs. So one tries to prove the presence of bugs and the other tries to prove the absence of bugs, and we will see in a minute how it does it. So let's consider our DAT, simple XOR gate, 2 inputs, 1 output. And in formal verification approach, the engineer is supposed to describe the behavior of the design, the expected behavior of the design. And this is done in, again, system Verilog standard, using the system Verilog assertion subset of the system Verilog. And simply what we write here is assert. Assert means that's a property, and assert always y is equal to a XOR b. So this is what the engineer codes. And next thing is it is given to the formal tool. The formal tool uses its internal mathematical algorithms to prove or disprove this property, taking all the possible combinations into place, all the possible states that the design can have, all the possible input combinations. So if this property is proven by the formal verification tool, then it is exhaustively verified and there is no possibility of having a bug there. So if it is proven correct, then the formal verification proves that there is no bug in the design or proves the absence of bugs, and or otherwise it will disprove this property that in this particular case, in this particular combination of input, this property does not hold true. So it proves or disproves this property, and this is the only input from the verification engineer that needs to be given. Rest is done by the formal tool. So here in this approach, we don't need any tests. No test benches are needed. No stimuli is needed. No simulations need to be run. Only expected behavior needs to be given to the tool, and the tool does the rest. So this is fundamentally different approach to verification. Now it seems too good to be true, right? We don't need simulation anymore. We have formal verification. Who needs simulation? I can just give assertion and prove, but it doesn't work like that. In SoC verification, of course, it doesn't work like that because in formal verification, as the size of the design increases, the number of inputs and outputs increase, the number of states that the design can reach also increases. So all this data starts to explode at certain time, and then we reach into capacity issues where formal engine says that I cannot handle it anymore. I cannot prove or disprove your properties that you've given me. So it cannot handle currently designs of big size, and we cannot just give a complete SoC with assertions to formal tool and say that prove or disprove it. and I'm done. So how it is used? So formal verification is used in certain cases in majorly smaller designs. So we select that areas of SoC which are likely to have more bugs, and we need really high quality verification, but it's also small enough for formal verification tool to handle. We use formal verification for that portion. And also if there is massive connectivity in the SoC, sometimes for visibility we have to mux out different inputs from different points in the design and bring them to the pads in order to be able to debug the silicon. So for that, there is massive muxing structure. There is a lot of inputs which have to be verified that everything is connected correctly. So this kind of verification is handled very nicely with formal tool. We can just write assertions. If mux input is this, your signal A should be connected to signal B, and that's how you verify thousands of mux connections very effectively using a formal tool. So this is what it is commonly used today. But with improvements in formal verification technology, in future, more and more verification will shift from simulation to formal. Let's discuss another popular verification approach, which is assertion-based verification. So let's try to understand using a simple example. Let's say we have a design under test, simple request grant kind of handshake. So whenever, let's say a spec says, our specification says that whenever we see a request on some clock edge, then within the next 3 clock edges, you should give a grant. The design should give a grant. And this is the specification that we want to verify. Very simple. This can be verified using system Verilog code. We can have something like this, always at whenever request, grant, and then we can have a counter of 1 to 3 clock cycles, clock edge. If grant is okay, then we say okay. If grant is still 0 at the end of 3 cycles, then we say it's an error. You can have this complicated code. Or you can do the same thing using system Verilog assertions in one line. So this is the power of system Verilog assertions. It is a subset of system Verilog, a specific language which allows us to describe the properties of the design, the behavior of the design. In XOR case, we saw assert y is equal to a XOR p, simple assertion. In this case, there is a complex behavior for which you would require a complex checker. But instead of that, you can use system Verilog assertions to just say, just describe a property at passage clock. If there is a request, then in following 1 to 3 cycles, there should be a grant, and assert it. So when this is run in simulations, it will work similar to this code and check this behavior. And this same assertion can be given even to formal tool to prove or disprove informal verification. And SVAs or system Verilog assertion is a very popular method in writing, in describing the design using very crisp and small code and achieve the verification very quickly. So this is assertion-based verification. Now, we have seen the verification approaches, test benches, test cases. How we measure verification? How do we really know how we are progressing? What is the quality of our verification? So this slide talks about that. What is our aim? Verification aim, if you see at a very high level, it's two things, right? So first thing is, we have a set of specifications. We want to ensure that all specifications are 100% covered in our verification. That is one aim. Second aim is that the actual design, the way it has been coded, that should be 100% covered. As long as both these aims are met, we can say that we are good in verification, or our verification is good quality. So how this is done? When we have done test benches, tests, etc., and we run simulations, then there is an option also to generate a coverage database, and that can be loaded into the coverage analysis tool. If you remember, this is one of the minimum set of tools that we need. So it is loaded into coverage analysis tool, and this analysis can be done. How do we cover the specifications? So specifications are covered by what we call as functional coverage. So looking at this functional coverage, functional coverage models are coded by the verification engineers. And this is an example of UART functional coverage model. If you remember the spec, 5 characters, 2 baud rates. So functional coverage model would simply look like this. You have a cover point. These are all syntax. So you have bins for the characters, 5 characters. You have bins for 2 baud rates, and then you do a cross between these two, and you run your tests, and it tells you that whether you have hit all the 10 combinations or you have not hit all the 10 combinations, and then you can adjust your tests, add tests, modify tests to hit all the combinations. So once you get 100% coverage on this model, you are sure that your specifications are 100% covered. Next is how to ensure that your actual code is covered. This is also called structural coverage. So this tells us, this gives visibility into how much of the code, lines of code, are we actually exercising using our existing tests. So in this particular example, if you see, the green code is covered by the test and the red one is not, which tells you very simply that in your stimulus, you have not set b equal to 1 ever. So you would add a stimulus or modify your stimulus in a way that now exercises this branch of the code as well. And also the code has never reached else branch here. So you can again modify your code to reach these uncovered branches. And once you have 100% of code coverage, meaning that you have covered whatever has been coded, also 100%. And this gives you coverage on the DUT, 100% covered. So once you have visibility and measure of how much of specifications are covered or how much of code is covered, you can add and modify your verification to achieve 100%. Quality metrics and sign off. So how do we know when we are done in verification? When can we give a sign off? RTL code coverage of target portions of the design. So must be 100%. As we discussed, code coverage must be 100%. Functional coverage must be 100%. All tests must pass, of course. All assertions must pass. If you're using assertion-based verification approach, low power simulations must pass. If this is applicable to our verification problem, formal verification results must be clean. Selected tests must pass in gate level simulations. Gate level simulations was covered in part 1. So this should pass. And these are all the quantitative criteria that we see to sign off on verification. And finally, there is also a gut feel, engineering judgment. After doing all these quantitative things, the overriding thing is that whether the verification team or the verification lead has a good gut feel and a good feeling of everything having been covered in a thorough and a very high quality way. And that's how this final sign off is given. So which includes the things that can be measured, and also the judgment portion, which cannot really be measured in numbers, but it is a feeling of completeness, that everything has been done nicely. And combination of all this can lead to a sign-off of verification. Emerging trends in tools especially. So if you see SoC specification to tape out, this is the SoC development cycle. And majorly two things are happening there: RTL development during initial phase, and then this RTL is synthesized and converted into physical implementation towards tape out, and which is manufactured later. Verification spans right from the day the specification is available to the tape out. It spans the entire development cycle. And what is happening during this time is major activities are test development, debugging of tests, because the RTL will have initially issues and bugs, and which verification team has to find and debug and find. Then there is also called regressions, which are continuing throughout the verification process. We keep on adding tests to that regression and run that every time there is a new RTL release given to the verification team. So that we call as regressions. And coverage closure, as we discussed, we should reach 100% mark. So we had traditional tools, but now AI is finding its way into tools itself. So what we are seeing in the industry is that tools are getting developed using AI algorithms to help in these topics, especially debugging. So there are tools that will actually analyze the waveforms over several runs, and then try to predict which portions of why your test case has suddenly started failing, or what are the hotspots of the design that could have bugs. So all this is being enabled using AI-based tools, and also coverage closure. So tools are there which help in coverage closure faster. That means that if you needed 10,000 tests to close your coverage, but that can be optimized and can be done in, let's say, a few thousand test cases only. So you don't have to spend time running 10,000. You can optimize and do it using less number of tests. So that is, again, there are AI tools for that. And the general trend that we are seeing is that AI-based tools are being developed, and they are also now available for use, for evaluation. And the promise is that they will help in each of these cases, and make the verification process even faster and more efficient, and thus, in certain cases, directly affecting the development cycle. Finally, I will close with sharing some observations. Uh, Functional verification, of course, it's a very important functional area, and success of the product depends on it. We discussed this already so much in detail. Verification can be limitless. So it's very, very important upfront in the design cycle to define a good strategy. We have choice of test benches, we have choice of techniques, to choose the right techniques and the right approaches upfront to be able to finish verification in the limited time that is allocated during the project development cycle. And if this is not done, then verification can there is a risk that it will not complete in time, and it can theoretically be a limitless process. You can be verifying for years together if this verification strategy is not defined upfront. Very important. Verification is highly subjective, so of course it needs skill, and it depends upon the person who is verifying that area. It depends upon the imagination. It needs a lot of creativity in order to find corner case, and difficult to find bugs. So it is very, very subjective skill, and skill develops over time and with experience. It is a people intensive domain. So typically in a project team, we could have 40% of the team which is dedicated to verification only. So a lot of people are needed in this domain. Last 5% is usually the hardest to achieve. So it's it's people who are familiar with this domain will say that okay, we can go till 95%, but to achieve that last 5% of coverage, like last 5%, and go to 100% is really what sweats people out. So this is what verification is. And and just learning the languages, tools, techniques is not enough. So you may be an expert of system Verilog, UVM, you may be able to churn out test benches, but in order to be a good verification engineer, one should have knowledge of other aspects also, the design, the physical aspects of the actual chip, and the entire knowledge of the VLSI process, and not just limited to the tools, etc. Because verification engineer will encounter problems or bugs that actually affect the silicon directly, and we should know how it affects silicon without affecting functionality. There may be cases where functionality is not impacted, but let's say there could be a high power drain in actual physical device. So one needs to know how things are linked. And finally, engineers need to have good understanding on all the three aspects that we covered in this presentation, and the one before, the why, what, and how. So that brings me to the end of this presentation, and now we can open up for any questions, comments.
Yeah, thank you so much, Mr. Singh, for giving us this informative session on how part of SoC design verification, and like to us, to our viewers, or no, to our current viewers, or to our future viewers as well. So maybe we can just take up a few questions. So okay, so we would like to start with something on these project deadlines. So say for that students working on their dissertation thesis, or these young professionals who have just got into the industry, and then when these deadlines comes, there's a kind of chaos in their life. So like how should they manage the trade-off between the thoroughness and the time efficiency in verification process for meeting the project deadlines?
Yes, so this is very relevant question, because see, deadlines will be there in actual projects for sure, and almost always close to deadlines, there will be a semblance of chaos, right? So there will be like everything has to be done very quickly. Um, this will be there for sure, but the way to handle it is that with skills, right? So over time, you should develop good understanding of languages, of skills, and develop debugging skills, basically. So and have a structured process to debug. So normally in times of stress, we don't really follow a structured approach. We just try to do hit and trials, and that is counterproductive. So if you just calm yourself down and think, why this could be happening, or what could be the cause of this failure, step A, B, C, D, and go in a very structured approach, most likely in your first trial itself, you will reach the root cause, and that is what is needed. So debugging skills and skills with your tools and techniques, this you should invest in, and always
Thank
stay
you.
calm. Always stay calm.
Yeah, I think that's the major mantra.
Yes,
Don't get distracted or don't get overwhelmed.
yes. There will be stress, by the way, always.
Thank you. So maybe we can take the next question, that how like should we ensure that what are the major challenges or bottlenecks that are typically encountered during SoC verification? If you could throw quick some light on that, so that will be helpful to our viewers in the long run.
Bottlenecks are sometimes there is a problem to reach the coverage, because the way the design has been coded, you are trying to reach 100% coverage, but you see that in a particular state machine, a particular state arc is not getting covered, a particular line of code, no matter what you do. So you have tried your best, but you're still not able to create that scenario to hit that line of code. So this is a very common problem that comes, and it also comes during the end phase of the project. So here, what is needed is to align and to discuss with designer, because the designer who actually created the RTL, and together figure out a scenario on how that particular line of code or that particular area of the RTL or HDL can be covered in your this. So a very strong alliance with the designer is needed for achieving this. This is one. This is one, and there may be others. There are many others also.
Thank you, Ravinder, for sharing this with us. So maybe like before we close, I'll just request that if you have anything else to say to our to this future professionals, or anything, any mantra you would like to share with them, or any two liners.
Yes, yes. So sure. So uh, uh, I think chip design industry is really a sunshine sector now, and there is a lot of focus of the government as well as on this sector, because it's a strategic sector. So this is, so if you are considering chip design as your career, it will be a really a good choice to you. And on especially on verification, I would say that it is very frankly, it's not for everyone. Okay, so if you are the person who really values the quality of the end product, right, who really appreciates quality, and so verification is for you, and who likes to know how things actually work inside. If you open an electronic device, you see a small black square of plastic there. If you want to know how that plastic is working and making your entire appliance work, now what is the interaction of your hardware and software, and if these things really excite you, and so verification is for you. So with verification, you will actually know the architecture of the SoC, as well as you are able to know things functionally, how they actually function, because you're writing code for it. So you know how hardware, software interact, and what is the architecture, and how this small square of plastic is doing magic for your
So thank you so much for sharing these concluding lines with all of us. So maybe on behalf of everyone, I would like to thank you from core of our heart to provide us such enlightenment sessions on what, why, and how part of SOC verification. For sure, we are very much pretty sure that this thing will these sessions which we have, where you have given your time to us, given your knowledge, shared your experience with us, that will for sure help these young professionals, help the students, help the faculties in the future.
Thank you,
So thank
Sushman.
you,
I certainly hope so. Thank you, and
thank you so
all the
much.
best to everyone.
Thank you everyone for joining us. So we'll catch up again next month.